Good day everyone, my name is Limbi Gui. Today I am present my final year project titled Design and Optimization of a Dual-Band Miniaturized Fracture Implantable Antenna for Fat Intra-Body Communication. To provide some context, implantable medical devices are widely used for continuous health monitoring. However, body tissues are complex electrical properties that make wireless signal transmission challenging. Among these various tissue types, fat tissue is unique because it has low permeability and conductivity. This leads to the concept of fat intra-body communication, fat IBC, which uses the body fat tissues as the transmission medium. To achieve the reliable transmissions, a dual band ensures frequency stability and compatibility with ISM bands for data transfer. To make the antenna small enough to be safely implanted, I am using a miniaturization technique based on fracture geometry, specifically Hilbert curve fracture, because this geometry allows us to pack a long electrical length into a very small physical area, maximize both bandwidth and efficiency inside a multi-layer tissue phantom. The motivation behind this research is clear. The World Health Organization states that chronic diseases cause 41 million deaths every year, accounting for 74% of total fatalities and significantly straining healthcare resources. This is the need for implantable medical devices such as pacemaker, insulin pump, and biosensors are increasingly used to monitor chronic conditions. The implantable antennas inside this device must be incredibly small to ensure patient comfort, yet highly efficient and stable enough to operate under varying tissue conditions. To tackle these challenges, my project is driven by three core objectives. First, to design and optimize a fracture-based implantable antenna using CST microwave studio for dual bandwidth for fat IBC. Next is to physically fabricate this optimized antenna layout, and third, to practically analyze and validate its transmission performance in a multi-layer tissue phantom. In my literature review, I analyzed the current state of the art for fracture implantable antennas. As shown in the table, previous studies have explored various mediums like muscles and skin. My proposed design fills a specific gap. It operates directly within fat tissue at a dual band of 2.45 GHz and 5.8 GHz by 7.5 by 10 mm design. Similarly, when reviewing antennas strictly designed for fat IBC, most existing solutions rely on standard patch, mended lines, or shorting pins, and I introduced the fracture Hilbert curve into the fat IBC space. This diagram illustrates the boundaries of my scope of work. The software simulations relies entirely on CST Studio, focusing on the dielectric properties of fat, skins, and muscles. The hardware will be fabricated on a high-frequency Rogers substrate, and we are targeting the dual band frequency, which is 2.45 GHz and 5.8 GHz. Finally, validation will be conducted using a vector network analyzer (VNA) connected to a 3-layer skin fat muscle tissue phantom, where we will extract all parameters. My project timeline is structured into 3 distinct phases. Phase 1 is purely analytical, designing the fracture geometry, simulating it in CST, and optimizing it for low bandwidth and low specific absorption rate to ensure the tissue safety. Phase 2 is transition to hardware, focusing on fabricating the antenna and testing it inside a fat equivalent phantom. Finally, Phase 3 involves evaluating the communication performance and characterizing the antenna for real-world biomedical applications. Designing an antenna for biological tissue is vastly different from free space. While the standard free space wavelength at 2.45 GHz is 122 mm, placing the antenna inside the body changes everything. So we must calculate the effective dielectric constants, taking into both the substrate permittivities and the fat tissue relative permittivities. Because biological tissues have a high dielectric constants, our effective permittivity reached roughly 7.99 for the 2.45 GHz band and 7.82 for 5.8 GHz band. Because of this dielectric loading effect, the wavelength inside the fat tissue is drastically shortened. Using the guidance wavelength formula, the effective wavelength dropped from 122 mm to 43.2 mm at 2.45 GHz and down to 18.6 mm for 5.8 GHz. To fit the required electrical lengths into our miniature footprint, we generate the Hilbert curve factor. The total electrical length is approximated by multiplying the number of segments by the segment length d. As the factor order n increases, the complexity of this geometry increases exponentially, allowing us to squeeze a very long conductive path into a tiny area. Applying these equations to our 7 by 7 mm design space reveals the power of the factor. By the time we reach the fourth order iterations, the structure contains 255 individual segments. We also packed 117 mm of total wire length into a square that is less than a centimeter wide. To ensure the maximum power transfer and minimal signal reflections, impedance matching is critical. Using CST calculators for a core planar waveguide with ground and factoring in the Roger substrate with a permittivity of 10.7, design the fit line width and gap to achieve a near perfect 50.53 ohm impedance. Here is the physical simulation setup. The antenna is embedded within a realistic 3-layer block representing human skin and muscle tissues. This ensures our simulations account for the several signal attenuation caused by human biology. Let's look at the design evolutions. This is the first order Hilbert curve. As expected, the electrical length is too short. The S parameter graph shows poor return loss and is failed to resonate anywhere near our target ISM bands. Moving to the second orders, the trees become more complex. The increased length shifts the resonance frequency lower, showing a dip around 3.9 GHz. In the third order design, the dual band characteristic begins to emerge naturally from the fractal geometry, with resonance forming near 3.1 GHz and 8.3 GHz. This brings us to the fourth order iterations. These indicate Mendel's line perfectly maximize the electrical length within our strict 7 by 7 mm limits. To lock in the exact frequencies, I perform a parameter sweep on the segment length d, which controls the capacitive coupling between the trees. When d is 0.42 mm, the first resonance hits 2.45 GHz perfectly, but the upper band shifts slightly past 5.8 GHz. Conversely, if we increase d to 0.5 mm, the resonance shifts further away, completely missing 2.45 GHz but reach 5.8 GHz. After rigorous optimizations of some parameters, setting d to precisely 0.41 mm yielded the ideal result. As you can see on this final S parameter plot, we achieved excellent impedance matching with distinct dips exactly at our target ISM bands for 2.45 GHz and 5.8 GHz. Validating this result, this slide shows the surface currents and H field distribution at 2.45 GHz. Continuing with 2.45 GHz, the far-field directivity plot shows an omnidirectional radiation pattern. This is highly desirable trait for implantable sensors as it means the antenna can communicate with an external receiver regardless of the patient's physical orientations. Moving up to the 5.8 GHz bands, the surface current concentrates in different tighter sections of the structure. The far-field directivity for 5.8 GHz demonstrates a solid mean log magnitude of 2.25 dBi. Despite the high loss environment of the fat tissue, the antenna successfully pushed the signal outward, maintaining the efficiency. I anticipate a few challenges. Fracture antennas inherently possess a high Q factor which narrow the bandwidth. Furthermore, transitioning from simulation to real non-uniform biology tissues introduce risks of dielectric detuning and signal attenuations. However, overcoming these challenges yield immense practical value. In the biomedical sector, this antenna acts as a crucial bridge for remote continuous patient monitoring. Commercially, a successful prototype presents strong patient and licensing opportunity for medical device companies developing the next generation of smart implants. Ultimately, this research directly aligns with the United Nations Sustainable Development Goal 3, good health and well-being, and, and Sustainable Development Goal 9, industry, innovation, and infrastructure. These are the key journal papers and articles from the literature that guided my design parameters, tissue models, and methodology. To conclude, this project successfully proved through rigorous CST simulations that a fourth-order Hilbert curve fracture can miniaturize an antenna down to just 7.5 by 10 mm while operating highly efficiently at both 2.45 GHz and 5.8 GHz within human fat tissue. Thank you.